There's lots of different parametric equations you could use that describe the exact same path through space. Those are called different ways of parameterizing a curve. So let's take y equals x squared. What makes this parabola distinctive is this relationship between y values and x values. And you can see it numerically, and the algebra just reflects the numerical relationship. The y value is always the square of the x value for every single point on the curve. And that's exactly what the algebra is saying. The algebra is saying literally the y value is the square of the x value. And that's kind of why the algebra makes sense. Okay, so if that's the relationship between x and y that we want, what does this have to do with parametric equations? Let's pretend that the x-coordinate is given by some function of time, t cubed. So what should the y-coordinate be if we want to make a parabola? Well, we know that parabolas, the y-coordinate is always the square of the x-coordinate. So if the x-coordinate is calculated with t cubed, then the y-coordinate should be that same x-coordinate squared. And if you were going to write this in a more conventional way, you could say that the x function is t cubed and the y function is t cubed to the second power, which is the same thing as t to the sixth. So this would be one parameterization. This is a 6, by the way. So this would be one parameterization of a parabola. What if the x-coordinate is negative 5t? So that's how I'm calculating x-coordinates. The y-coordinate should be negative 5t squared, because I know that whatever the x-coordinate is, in order to make a parabola, the y-coordinate has to be that squared. And so that gives you another set of parametric equation. So far we've got t squared and t to the sixth, and that makes the exact same curve as negative 5t and 25t squared. All right, what if the x-coordinate is calculated as sine of t? What should the y-coordinate be? It should be sine of t quantity squared. But this example is not like the others. Well, here, let's write it out as a parametric set of equations, and then I'll tell you why it's not like the others. I said for all of these that the x-coordinate is produced as some function of time. But let's think for a minute about what each of these graphs look like separately. The t cubed graph looks like this. So I can see that if I'm allowed to have time be whatever I want, I'm going to get all possible x values, because the range of the function, the set of output values of the function, covers all x values from negative infinity up to positive infinity. And the same thing is true of negative 5t. Clearly, if I want to know, like, when is the x-coordinate equal to 1, it's going to be equal to 1 at different times depending on this function. So, like, for this parameterization, at time equals 1, the x-coordinate is 1. But for this parameterization, time needs to be negative 1/5 in order for the x-coordinate to be 1. So depending on what your equation is for calculating x as a function of time, you're going to hit different x-coordinates at different times. But the point that I'm trying to make is you can see by the set of outputs that you're still going to hit all possible x values. But now, what about the sine function? What you know about the sine function is it's not possible for it to output a value larger than 1 or smaller than negative 1. But if that's supposed to tell us what the x-coordinates are, what that means is that no matter what time you plug in, the x-coordinate has to be between negative 1 and positive 1. So for this parameterization, because of the way that we're calculating the x-coordinate, we're never going to have x-coordinates outside that range. So what overall effect is that going to have on the parabola? Because I thought that we were saying that all of these parameterizations make a parabola. If we were going to write this out as a table, I've got different times, and I'm using degrees here because I know not everybody's comfortable with radians yet. So the x-coordinate would be sine of 0 degrees, which is 0. Sine of 90 degrees would be 1. This is back to 0, negative 1, and 0. So that's just a description of, well, let's sketch it. So that's a description of this. And then the y-coordinate, I said, is always whatever the x-coordinate was squared. So I'm going to take that output from sine t and I'm going to square it. So 0, 1, 0, 1, 0. All right, so what's happening here? I've got a point at 0, 0, and then it's going to move to a point at 1, 1. And I didn't trace out the intermediate values, but you know that the intermediate values have to form the shape of a parabola because of this relationship where the y value is always the square of whatever the x value is. And then starting at time 180, starting from time 90, it looks like the x-coordinates are going to start going back towards 0. So the y-coordinates are going to start going back towards 0 also. And then from 180 to 270, the x-coordinates are going from 0 to -1. So it's still going to trace out a parabola, and we know that because of the relationship between x and y. But what the parameterization is doing is it's telling us information about how the path is getting traced. And the fact that sine of t can't ever output values greater than 1 or less than -1 means that the entire rest of the parabola will never get drawn because my x value will never become greater than 1 and will never be less than -1. So it's still a parabola, but it's just a parabola that's been restricted to the domain x is between +1 and -1. So that's another thing that the parameterization can do, is it can restrict the domain of the full curve that you might be drawing. I hope that you made a connection back to the previous video. If I wanted to rewrite any of these parametric equations in rectangular form, I could eliminate the parameter, just like we did in the last video. So I've got x is sine of t, and y is sine of t squared. So if x is sine of t, then that means I can substitute x in for sine of t, because they are literally equal to each other. So instead of saying y equals sine t squared, because sine t is the same as x, I can make the substitution and say that y equals x squared. So now I've gone both directions. I chose an arbitrary function to describe my x-coordinate, and then I said my y-coordinate should be whatever that was squared. And then I took that, and then I combined them back together again by substituting x in for the function that x was calculated with. So, time for you to try it. What if we wanted to come up with several different parameterizations for y equals 2x plus 1? So the relationship between x and y is whatever the x-coordinate is. To get the y-coordinate, we multiply by 2 and add 1. So let's pretend that the x-coordinate is described by t squared. What should the equation for the y-coordinate as a function of time look like? That's right. It's the x-coordinate times 2 plus 1. Let's do another one. What if the x-coordinate is described by the square root of t minus 2? What should the y-coordinate be? Yep, it is 2 times the x-coordinate, root t minus 2, plus 1. Okay, bonus question. This parameterization won't actually trace out the entire path of the line. So what's the domain of the line that this will actually trace out? And the answer is x greater than or equal to 0. So it's only going to trace out this part of the line. The reason why is because if you think about this graph, here's time, and here's the x-coordinate. This is a right-shifted square root function. So the smallest thing time can be is 2, but time doesn't really affect the path here. So what I'm really interested in is what are the x values that I can get? And you can see the range of this function only covers x values that are greater than or equal to 1. I can't get any negative x values. So what that means is that the part of this graph which has negative x values will never get drawn because there are no times which would produce the negative x values which might draw that part of the graph.